We have example 3 to finish up from yesterday. We talked about a couple different directions to go with this problem, if you recall, because we talked about using the Pythagorean identity that's sine squared plus cosine squared equals 1. We also talked about using sine to find cosecant, and then we used the cotangent cosecant Pythagorean identity. Regardless, at this point we have cotangent, we still need to find secant. So in looking at your identities at the top of the page, did you come up with any thoughts of how we could maybe find secant here? Huh?
Could you get the inverse of cotangent to tangent and then do tangent squared is equal to secant squared?
And a plus 1 in there somewhere?
Yeah, plus 1.
Okay, so, and there's 2 ways we could go here. Okay. One option is that if we know cotangent, then we know tangent because that's reciprocal. And we could use the Pythagorean identity, that is the 1 plus tangent squared equals secant squared. That would be one option that we could do that. What's the other option? Or I shouldn't say the other option, another option. Okay, could we use a quotient identity? If you look up at number 1, we used a quotient identity to finish it off, didn't we? And here, if we know cotangent and sine, could we use that to find cosine, and then we know secant because it's reciprocal. Now, here's the deal. They're both going to get us to the right answer. Okay? Neither way is more right than the other way. They're both good options. It's a matter of what you see. It's a matter of personal preferences. It is what it is. Okay? In my notes, I used the quotient identity, and I think I did that at the time just because we'd already practiced with a Pythagorean identity, so now we could practice with a quotient identity. Okay? So, again, both are good. So, I'm going to go the route, as I said, because just to practice, with the quotient identity. So, cotangent of theta is cosine theta over sine theta. And as I said, I'm not saying that we can't use the Pythagorean identity also. Okay, if we fill this in, what do we already know? We know cotangent is root of 5 over 2 equals cosine, which is what I'm trying to find, yes? Cosine of theta over sine of theta, and sine of theta was originally given as negative 2 over 3. Okay, how do we solve here? If it's cosine divided by something, we're going to multiply by something. So we're going to multiply by, if it's cosine divided by negative 2/3, we want to multiply by negative 2/3. The negative 2/3 are going to cancel each other, yes? Dividing by negative 2/3, multiplying by negative 2/3, those cancel. I'm going to reverse this, so I'm going to have cosine of theta. On the other side, what happens when you multiply negative 2/3 and square root of 5 over 2? The 2's can cancel, yes? And so what do we have at that point? Negative square root of 5 over 3. Now, what were we asked to find?
Secant.
We're asked to find secant. What's the relationship we know? If we know cosine, secant is the reciprocal. I am perfectly fine with, okay, here's cosine, making your next line written as secant. Okay, if cosine is negative square root of 5 over 3, what's secant? Negative 3 over square root of 5. Okay. Could you get fancy like we did on step 1 here and use the reciprocal identity also? You can, but you don't have to. Okay, I'm never going to require you to write out the reciprocal identity. If you know one, you know it's reciprocal. Okay? Now, if you tried the Pythagorean identity, you should have gotten the same answer. Okay? The first handful of homework problems are like what you see here. Okay, the first few homework problems are like what we see here. The rest of the homework problems are like the examples we're getting ready to try on the back side. Now, I think I mentioned a little bit yesterday that I am giving just the odds as our first assignment in this lesson because it's going to take some practice, okay? Especially as we get ready to go into this backside where we're simplifying, it takes some practice being able to see where to start, being able to see where to go, okay? Being able to see the steps. You'll get there. It's going to take us a little bit of practice of learning how to do these things. Okay, so that's why I'm giving you the odds, and then I'll tell you up front, the next assignment is going to be the evens later on this week, just in practicing how to do these. So, as you flip over to the backside, there are 5 numbered pieces at the top. Now, I'm not going to call them steps, because they're not do this first, do this second, do this third. But they are 5 different options or suggestions of things to look for, places to begin. Okay? You don't follow them in order by any means. It's just a matter of what works and what applies. So, one option is, as we're trying to simplify these, create common denominators, combine fractions. So that's only going to work if you have multiple fractions, but you can kind of try and add the fractions. Another option is to separate the numerators by dividing each piece by the denominator. Again, that only works if we have a fraction, but maybe separate depending on the situation. The third option there is to factor or FOIL. So we'll talk about how to factor certain things as we go through this week. We'll talk about like product and sum. We'll talk about GCF. We'll also talk about taking 2 binomials and FOILing them. Okay. Another thing is to look for the Pythagorean identities. We have 3 Pythagorean identities, yes? You need to be familiar with what those look like. And what you'll often hear me say is anytime you see squared trig functions added or subtracted to other squared trig functions or 1, then those are Pythagorean identities and we can always switch them out. So for instance, if you see a sine squared plus cosine squared in one of our problems, what do we know sine squared plus cosine squared is equal to? According to Pythagorean identities, it's equal to 1. And so we can replace that. Okay? And then the final option is change all trig functions to sine and cosine. In other words, sometimes it's helpful to be able to switch all the trig functions so you're only working with sine and cosine and seeing what cleans up there. Okay, so those are your 5 thoughts. Our job is to simplify these. I'm going to tell you as you look at these, all of these simplify down to just one trig function. Maybe it's a trig function squared or just a plain old trig function, but they all simplify down to just one trig function. Okay? So let's look at example 1. Or excuse me, example A. Sine cubed x plus sine x cosine squared x. Okay. Think about your 5 options up top. Let's see. Create common denominators, combine fractions. That's not really an option because I don't have fractions on that example A, do I? Separate numerators by dividing each piece by a denominator. Again, I don't have fractions, do I? Factor or FOIL? Maybe. Look for Pythagorean identities? Maybe. 5. Change all trig functions to sine and cosine? Well, they're all already sine and cosine, aren't they? So, options 3 and 4 are your options to think about here. Any thoughts as you look at A? Okay. Could we factor out a sine of x? Okay. In other words, in this particular case, both terms have a sine x, don't they? So we are going to factor, and in this particular case, we are factoring out a GCF. Okay, we're going to factor out GCF. Now, you're going to see me off to the side as we go through today. Write in, like, what are the ideas? What are the steps we're doing? So these are some things to look for. Okay, so as we factor out sine cubed has a sign, and cosine squared has a sign. So I'm going to put sine x out front. What is sine cubed x when you divide out sine x? Sine squared x, right? It's the same thing as what is x cubed divided by x? It's x squared. So what is sine cubed divided by sine? It is sine squared x. Plus, what is sine x cosine squared x when I divide out sine x? What'd you say? Oh yeah, if we have sine times cosine squared, I divide out the sine, I'm just left with cosine squared x.
Is the first x, is that part of the square? Because you left the x on.
This right here?
No, on the first side.
This?
Yeah.
So sine cubed x is just saying that it's sine x times sine x times sine x. You can't ever write sine without some variable or number in it. Okay, we'll never just write sine. I often will say just sine. That's just, poor form on my part, really. But there's always a variable with it. Okay. Okay. We all followed the first step. We factored out GCF. Okay. We got to keep going. Do we see anything? What do we see? I can't tell if anyone said it or not, but okay. What is our first Pythagorean identity on our list if you flip back to the front page? Now, the front page used thetas, yes. Realize theta is a variable, x is a variable, y is a variable, t is a variable. Doesn't matter what variable we're talking here. It does not. Okay, so this page is x's, the front page is thetas. Just get used to different variables being thrown in. But if you look on the front page, it says sine squared theta plus cosine squared theta is equal to 1. We have sine squared x plus cosine squared x, and that is equal to what? 1. So we can take that and replace it with 1. And what is this that we're using? This is a Pythagorean identity. So this piece is going to become 1. Out front, we still have sine x. Okay, so we got, by factoring out the GCF, we could then see sine squared plus cosine squared. It becomes 1. What is sine x times 1? Sine x, right? When you multiply by 1, you just get what the other thing is. So sine x times 1 is sine x. You're at a single trig function, folks. You're there. Okay. Questions so far? It's the more we work with it, hopefully the more you'll get to start seeing these on your own. Okay, it just takes time and practice. Okay, let's look at B. Secant x plus 1 times secant x minus 1 over sine squared x. Do we see anything? Any thoughts? Okay, you can kind of go through, run through your, options up there for ideas. Okay. On top, we have a binomial times a binomial, don't we? Even better about those binomials is that they are what I would call conjugates, where they're the same pieces, opposite signs. which means multiplying them is going to make it nice. So yes, I would agree that we want to FOIL the top. So let's get to that. As we go to FOIL, what is secant x times secant x? Secant squared x. Now, hang with me on this. Outsides, what is secant x times minus 1? Negative secant x or minus secant x? Okay, what are my insides? 1 times secant x. Plus 1 secant x? What just happened? What's minus secant x plus secant x? Do they cancel? Right? Remember when you multiply and the middle signs are different, my middle terms cancel, don't they? And so then what's last? 1 times negative 1 is negative 1. So I'm going to rewrite this as secant squared x minus 1 over sine squared x. Okay. Now I need another step. What? Okay. We cannot take the square root in what we're doing here. And here's the reason, because this is a true statement with everything we're doing. We're not solving equations. If we're solving equations, there's a left and a right, and you take the square root of both sides to keep the equation equal. When we are working with an expression, square rooting the expression would change the value of it. Okay? So unless we're solving the equation, we can't square root. But good thing to talk about. So.
We need to change secant to cosine the Pythagorean identities.
Well, okay, so changing, so there's 2 points I want to make here. First of all, changing secant to cosine here would make this 1 over cosine, or 1 over cosine squared minus 1 all in the numerator. Because this minus 1 here, it would not just push the cosine to the denominator, which is what I think you were trying to do, maybe. I don't know. However, I do want to talk Pythagorean identities, just not the ones Zoe was thinking. Okay, and here's what I'm always going to say. When you see squared functions being added or subtracted to other squared functions and or ones, look for Pythagorean identities or Pythagorean identities that can be manipulated. Is there a Pythagorean identity that involves secant squared and 1? There is, isn't there? What is the Pythagorean identity that involves secant squared and 1? It says that 1 plus tangent squared x equals secant squared x. Yes? Did I get that right? Sometimes mix up my pieces. Now, this is kind of sidebar for a moment, because I need your brains to think. Can this be rewritten to look like secant squared x minus 1? Yeah, because what can we do here? If there's a positive 1, I can subtract 1 to the other side, and then we're going to have tangent squared x is equal to secant squared x minus 1. Is that something we have in our equation or in our expression? Secant squared x minus 1, secant squared x minus 1. What can I replace it with? Tangent squared x. Okay? So, it may not have been exactly a Pythagorean identity, but we could make it work, can't we? Okay? So, being able to add and subtract within your Pythagorean identities is important. So, I'm going to use Pythagorean identity. And we're going to rewrite. Instead of secant squared x minus 1, on top is going to be tangent squared x. Still divided by sine squared x. Okay? And again, me writing these notes off to the side, not required by any means. Just when you look back later, trying to give you tips of how did we get from step 1 to step 2 type thing. Okay? So we now have tangent squared x over sine squared x. We got to keep going. Any thoughts of how we could keep going? And, you know, my suggestions as we go through each step, you can always go back to the top 5 things and look for more ideas there. You can also go to your all your trig fundamental identities on the front page and look for ideas there. Okay, those are the places you're going to get your ideas.
Yeah. Like you can move. Wait. Yeah. Subtract the sine squared of theta and whatnot.
So replace sine squared with 1 minus cosine squared.
Oh, wait, no.
I mean, it's equivalent.
Squared.
Are you looking at something? I'm confused on what you're doing, but
We're not on blue.
no, we haven't finished B yet. That's where, okay, I was so confused. No, we're not done with B. B comes down to a function squared. I'm not at a function squared. I'm at a function squared divided by a function squared. But remind me to make a point about what you said when we get to C, because you did have something we need to point out. Okay.
Would you let's use the quotient identities?
Okay. I would suggest we use the quotient identity here. In terms of, we can get rid of tangent and it changes it to sines and cosines. And so with the idea of kind of idea 5 here, change all functions to sines and cosines. Now, officially our quotient identity says tangent is equal to sine over cosine, yes? Realize that works also for squares. So tangent squared is going to be equal to sine squared over cosine squared. So we are actually going to do that. So tangent squared is going to be rewritten as sine squared x over cosine squared x, and then it's still divided by sine squared x. So that right there is using a quotient identity, or changing everything to sine and cosine. I know, it's getting uglier, not better, but I promise it is getting better. We're actually there in one more step. Maybe 2, I guess. What are we doing here? This is a fraction divided by something else, or could I say a fraction divided by a fraction? How do we do fraction divided by fractions? Okay, multiply by the reciprocal.
The sine squared cancel out.
Okay, somewhat, yes. Okay. Yes, the signs are going to end up canceling, but you have to know what the results are, which is why I say be careful, which is why I'm going to take us the direction of it's a fraction divided by a fraction. So I'm going to write this out so we can see it. So it's a fraction, sine squared x over cosine squared x, divided by a fraction. What do we normally do? We multiply by the reciprocal. So when you do your keep change flip, You have sine squared over cosine squared. Instead of divide, we're going to multiply. And instead of sine squared over 1, it's 1 over sine squared. Now, do our sine squareds indeed cancel? They do. Here's the key. What remains? 1 over cosine squared x. You will not see 1 over cosine squared x anywhere in the answer key, though. They will not leave a trig function in the denominator. What is 1 over cosine? Secant. Cosine is a reciprocal of secant, yes? So 1 over cosine squared is secant squared. Secant squared x. Okay? It's looking for those steps. Sometimes they're easy to see, sometimes they take a little work. Okay. We're going to do C, and then I want to make sure we look at E. E is, it looks different, but it's actually, I kind of like it. I think it's a little bit easier than some of these. Now, as we go look at C, okay? Tate was looking at C earlier. He was jumping the gun on us. But when Tate looked at C, he saw 1 minus sine x. And I don't know if you guys realize what he was trying to do. He was trying to use the Pythagorean identity. Why can I not use Pythagorean identity on 1 minus sine x? Because there's not squared. Pythagorean identities only work when there are squareds involved. FYI there, okay? So, we need to take a different route because Pythagorean identity does not play a role in this one at the beginning. What's an option? Well, you said, can we cancel? I don't know if this is exactly what you're talking about, but I'm going to use it as a point. Can we cancel those cosines? Okay, here's the deal. What are we doing? We are subtracting. Does cross cancel a thing when we subtract? No. When is cross canceling a thing? When you're multiplying. Are we multiplying these fractions? No. So you cannot cross cancel. But I'm going to get that out of the way. My morning class did that too. So I'm trying to, if nothing else, dispel some mistakes or myths. What about, we have two fractions being subtracted. How do we make them one fraction? If we're subtracting two fractions, what has to be true to add and subtract fractions? You need a common denominator. So, idea number 1 might not be pretty in the meanwhile, but that's what we're going to do. So we're going to get a common denominator. My current denominators are 1 minus sine x and cosine x. What's a common denominator between 1 minus sine x and cosine x? Do they really have anything in common? No, so common denominator is smush them together and 1 minus sine x times cosine x. Or cosine x times 1 minus sine x. So, let me write this out and then we'll do the work. We're going to have two fractions being subtracted. Common denominator, I'm going to write as cosine x times 1 minus sine x. Cosine x times 1 minus sine x. Okay? First fraction. The common denominator is supposed to be cosine times 1 minus sine. What is my first denominator missing? It's missing the cosine in the denominator, yes? If I have to multiply the denominator by cosine, what do I have to do to the numerator? We're going to multiply it by cosine. So So first fraction, we're multiplying by cosine over cosine to get that common denominator. On top, what is cosine times cosine? Cosine squared x. Okay. Second fraction. My denominator is cosine. What am I missing from the common denominator? I'm missing 1 minus sine x. So I multiply the denominator by 1 minus sine x. We're going to multiply the numerator by 1 minus sine x. So, now, are you guys willing to go ahead and multiply those numerators? How do we multiply sine x and 1 minus sine x? We're going to have to distribute. Sine x times 1 is sine x. Sine x times minus sine x is minus sine squared x. Okay, that's distributing. Now, I got my common denominator, yes? I have two fractions being subtracted with a common denominator, so we're going to put it together into one fraction. My denominator of this fraction is cosine x times 1 minus sine x. And I will tell you, you will notice I don't often multiply my denominators together unless I have reason to. Okay, I usually leave them as separate pieces. Now, on top, I got my common denominator, so on top we're just going to subtract, yes? So I'm going to have cosine squared x, and then what are we doing? We're subtracting sine x, and then what else am I doing? Subtracting negative sine squared x, which makes it adding sine squared x. Okay. What? Not exactly, but why? Because I think you're on the right track.
Because it was negative 1 was like plus 2.
Wait, what are you talking about?
Like the negative sine x plus sine squared x.
No, because that would be adding like negative x plus x squared. They're not like terms.
Can you cancel one of the cosine?
Can I what?
Can you cancel like one of the cosine squared x's and not a cosine?
I cannot cancel a cosine in this form. This cosine on bottom could be cancelable, but this cosine on top is not because it's not a factor. When you're adding and subtracting pieces, you can't just cancel a piece. You have to cancel factors that are multiplied together. So I could cancel a cosine on bottom, or I could cancel 1 minus sine on bottom, but I can't cancel I'm trying to remember how I don't know. I think someone in the morning class just saw it. I don't think I gave a hint. There's some squareds. There's some squareds being added or subtracted.
So it's more.
Pythagorean identity.
Are they the pieces of one of our Pythagorean identities? Whether you can pronounce it or not, are there some pieces of the Pythagorean identities? Yes? Okay. Now, for the benefit of making sure everyone sees it, I'm going to rewrite. I'm going to reorder the front, or the top. Okay. So on top, we have cosine squared x, and then I'm going to write plus sine squared x, and then that pushes the minus sine x to the back. Still, all over cosine x times 1 minus sine x. Now, do you guys see the Pythagorean identity now that I've rearranged things? Right here. Cosine squared plus sine squared x is a Pythagorean identity. Okay? That can be replaced with 1. Okay, so let's rewrite that. So cosine squared plus sine squared x is 1. What else do we still have? Minus sine x over cosine x times 1 minus sine x.
Cancel.
Now you can't.
Okay, 1 minus sine x is a factor on bottom. On top, 1 minus sine x is all there is. So what can we do? We can cancel. Now, on bottom, what remains? We have cosine x on bottom. What remains on top? If everything cancels, there's always, by default, 1.
1. Oh. So it's
What is 1 over cosine x?
secant.
Secant x. All of a sudden, things just come together eventually. You just have to get to that point. Okay? Now, the other piece I said I wanted to do is I want to talk about E. Okay? We're not going to get through all the examples, but we're getting some ideas going. Let's look at E. Now, E is a little different, isn't it? I know I saw some weird faces earlier when I said I wanted to look at E, but I like E because I see those negative x's in parentheses, and my brain says, oh, those are identities. What identities have negative x's inside of them, or negative variables?
Even odd.
Okay, so we're going to use our even and odd identities, and I have parentheses that have pi over 2 minus x in there. What identities have pi over 2 minus x's in them? Cofunction. So we're going to use our even and odd and our cofunction identities to replace things. So, go to your identity list. Tangent of negative x is equal to what?
Negative.
According to my even and odd, if there's a negative in the parentheses on tangent, it's equal to a negative outside. So negative tangent x. Cosine of negative x. Cosine of negative x, according to my identities, is equal to
Positive.
positive. It's an even, so it's equal to just positive cosine of x. Sine of negative x.
Negative. Yeah.
You guys are going to this list, right? Sine of negative x is negative sine of x. It is odd. Secant of pi over 2 minus x is equal to cosecant
Oh, yeah, sorry.
of x. Now, we're not there yet, but it looks a little more normal. Okay, so we used our identities. That's what I used there. Now, we need to multiply all these. How about we do some changing? What can I change these all to? Let's change these all to sines and cosines. Okay? Change them all to sines and cosines. How does negative tangent change to sines and cosines? It's a quotient identity, right? So one of the ones we're going to use is a quotient identity. Negative tangent is still going to be negative. And it's going to be negative of sine x over cosine x. Cosine's already cosine. but I am going to make it a fraction. What is cosine as a fraction? Cosine x over 1. Negative sine x. It's already sine. What is it as a fraction? Negative sine x over 1. What about cosecant? Okay, cosecant has a reciprocal identity that says 1 over sine x. So we used a quotient and we used a reciprocal. What do you notice with all these fractions that we're multiplying?
They cancel.
A cosine in the denominator cancels with a cosine in the numerator. A sine in the denominator cancels with a sine in the numerator. What remains?
Sine x.
Okay. A negative sine x times another negative, yes? Negative times negative makes it positive sine x. Okay? It takes practice. Okay? My hope is by running you through these 4 examples today, you're starting to see it. Now, here's what I want you to do. Okay? Yes, I want you to do the odds for tomorrow. Now, when I say do the odds, I did the odds for a reason because you have the answers available to check. I want you to go through and attempt every problem. Am I expecting you to succeed at every problem?
Yes.
No. I would love to say yes. I hate being negative. But I'm trying to also be realistic with you. It's going to be a struggle on something. Okay? I want you to go through and try. My plan for tomorrow is to spend all period going over your homework questions. That is my plan for tomorrow, is we are going over homework questions. Okay? So, come tomorrow, have you attempted it, we will go over questions, and work for you guys to see these, okay?
How much? 1.3.